Molecular orbital theory, or MO theory for short, going to be the topic in this lesson. And this can be a real pain point for students, I'll warn you, but reality just happens to be more complicated than we'd like. And it turns out that MO theory here is going to do a better job of describing bonding than either valence bond theory or even the Lewis structures we've gotten customary drawing now. Everything has its utility, everything has its place, but it turns out this one actually gives the best description of reality. We'll talk about why H2, hydrogen is diatomic, whereas helium is not. And we'll talk about why O2 has some magnetic qualities that would not have been predicted, say, from the Lewis structure, but MO theory allows us to explain those. So super useful, but again, it's a little bit complicated, but we're going to hopefully bring it down exactly to a level that's understandable. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. And this particular lesson is a really good one for this to be my objective, so hopefully we accomplish the task. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. This lesson's part of my new general chemistry playlist. I'm releasing several lessons a week throughout the school year, so if you want to be notified every time I post one, subscribe to the channel, click the bell notification. All right, so we got to take a look at molecular orbital theory here, which is going to be pretty much our best theory of bonding. And everything has their shortcomings, and nothing's perfect, but this is the best description of reality you're going to learn in your general chemistry course here. And the truth is, it's actually more complicated than we're even going to get into it, but we're going to cover it at a level that's pretty much going to suffice for most all of you in a general chemistry course. So if we take a look at hydrogen here, so we'll start with valence bond theory, and then we're going to build on it from there and see what's really going on. So in molecular hydrogen, we saw with valence bond theory that if you've got two separate hydrogen atoms which have their unpaired electron in a 1s orbital, so that if these two atoms come and approach each other, you will get overlapping orbitals, and valence bond theory, just suffice it to say, says, yep, and electrons live in those overlapping orbitals, life is good. Well, it turns out it's actually a little more complex than that. So these atomic orbitals, these 1s orbitals in this case, those are wave functions. So don't forget that all your atomic orbitals are solutions to the Schrödinger equation. They are three-dimensional mathematical equations themselves we call wave functions. Well, it turns out when you overlap these wave functions, you can add them, or really a better word is combine them in different ways. So we're going to look at those different ways. Now, to understand this, though, we got to talk about some two-dimensional wave functions you're maybe more familiar with and talk about what happens when they overlap. So we're going to go back and take a look at the sine function from your trigonometry class for just a second. And if you took a look at a typical sine function here, we'll focus in on this top one first. So from 0 to pi, or which is the same as 0 to 180 degrees, so the sine function takes on positive values. But then from pi to 2 pi, or 180 to 360 degrees, it takes on negative values. But right there, right in the middle, so it takes on a value of 0. In fact, at every multiple of pi, it takes on a value of 0. And for a wave function, we refer to that as being a node. So it's just a place where the function has a value of 0. Now, the correspondence to that, as we're going to see when we're talking about orbitals, is there. For some of the more complex orbitals, it turns out there are no nodes in a 1s orbital, but for pretty much every other orbital, there's going to be a node somewhere. Like p orbitals always have a node at the nucleus. So, and for the function going to 0 for a wave function for an orbital here, that means you have a 0 likelihood of finding the electron there. So just keep that in mind. Now, if we have two of these sine functions, and they overlap just like so, where the positive parts are perfectly aligned and the negative parts are perfectly aligned, we refer to that as being in phase. So, and when you have in phase overlap, so when you basically they overlap, it's just plus with plus, and they add together essentially, and you get constructive overlap, and the function is amplified. And so the sum of these two when they're in phase like this is just a larger function. Cool, but you can also have it to where instead of having plus overlap with minus, or I'm sorry, with plus and minus with minus, you can actually have them exactly out of phase as well. So, and now when they're exactly out of phase and they have the same magnitude, they're actually going to cancel each other out in this case. Now, it turns out I've gone to the extremes here. I've gone exactly in phase and exactly out of phase, but you can have everything in between. So, but the extremes are all we're going to be concerned with here. But see, every value in the function here has a corresponding negative value here. And when you add them together, they add up to nothing, to 0. And so in this case, they canceled each other out. This is destructive interference. So, and this is going to be important when we start looking at adding wave functions, because it turns out your atomic orbitals, being three-dimensional mathematical equations, in some cases they're going to have positive values for the function, and in some cases they're going to take on negative values for the function. Now, one thing I want to point out on your sine function is that as you're going from an area where it takes on all positive values and you cross over to an area where it takes on all negative values, you do have to cross through 0 and get a node, and we're going to see the same thing when we look at the p orbitals, which have that node at the nucleus a little bit later on. So let's go back and take a look at these overlapping s orbitals for a second. So, because it turns out these s orbitals, the wave functions, again, these are just three-dimensional mathematical equations, can take on either positive values or negative values. And for the 1s orbital, it could be either one. It could be all positive or all negative. And so say that these s orbitals here are all positive. And so when they come to overlap, so then the region where they're overlapping, all the values are positive, and that region is going to get amplified in the same way that our sine functions were additive when they overlapped in phase. And so this region would get amplified, and what you'd end up with is you'd end up with a big, giant wave equation. That's kind of the combination of these two, where it's amplified right down the middle. And if we kind of draw in the nuclei right here, you'd find out, so again, these wave functions describe where an electron might be found, and it turns out it's really the wave function squared that describes that, but I'm going to gloss over that for now. You'll get that a little more in your OChem class or a PChem class. So, but in this case, the most amplified region here is this region right in between the two nuclei, right where the overlap was occurring. And so in this case, it turns out that's going to be the most probable place to find an electron. And that's a good thing because the nuclei are positively charged, the electrons are negatively charged. And so having this region right in between the two positively charged nuclei being the most likely place to find an electron, well, that's the place the electron wants to be most. And what we really mean when we say that, because obviously electrons don't want anything, but what that really means is that that's where they're going to be lowest in energy. So when they have the most attraction to the things they're attracted to, and they're closest to both. So that's right along there, and that's again now the most likely place they're going to be found. And so it turns out that these two original atomic orbitals have now combined to form this one giant we call molecular orbital, hence the name of the theory here, molecular orbital theory. So, and this molecular orbital is lower in energy than either one of the original atomic orbitals. For one, again, the electrons now get to see two nuclei, and the most probable place they'll be found is right exactly in between those two nuclei. And so that lowers the energy significantly. It turns out also, according to the Heisenberg uncertainty principle, that the larger the volume of an orbital, the lower its energy as well. And so in this case, this molecular orbital is larger than either of the original atomic orbitals as well. And so this molecular is going to be lower in energy. Now it turns out this is end-to-end overlap that's occurring here. That's sigma overlap we learned earlier in the chapter. And we'd refer to this guy right here as the sigma 1s orbital. So, and in this case, again, it's a molecular orbital. So we can see the atomic orbitals that we started with before bonding occurred, and now we can see the molecular orbital they've overlapped to create. Now, here's where things get a little bit weird. So we said that the atomic orbitals here, these s orbitals, can be either be all positive or all negative. And the result would be this sigma 1s, whether they've been both all positive or both all negative. We still would have got constructive overlap in either case. But what happens if instead one of them has the negative version of the wave function? Well, then when they go to overlap, instead of constructive overlap and amplification, we're going to get destructive overlap now, and it's going to cancel out this region right down the middle. And to draw this, there's a couple different ways you can approach it, but what I usually like to do is draw the same thing I drew down here. And then erase the part where they canceled each other out. And again, one side's going to be now positive, one side negative. You'll find out another convention we'll use, and we'll probably use it with p orbitals a little more, is that instead of writing in the plus and the minus, we'll actually like shade one and not shade the other, or shade one color and shade the other a different color. And so I'll use that convention a little bit too, because that's something you're likely to encounter. So, but in this case, this is one new, again, molecular orbital up here. So it has two areas of electron density, but it is one molecular orbital. So, and we have created a node right here where the function has a value of 0. And what that means, again, is that you're never going to find the electron right along that node. And recall, that's the actual best place an electron would want to be, right in between both of the positively charged nuclei. And that's the one place it cannot be. And so as a result, so if letting the electrons be exactly where they want to be lowers the energy, well, then not letting them be there is going to actually raise the energy. Also, because part of, again, we had destructive overlap, so the total volume here is going to be lower than the total volume down here where there was amplification. So because part, again, these original atomic orbitals that overlapped canceled each other out, so to speak, destructive interference. And so the overall volume of this lovely molecular orbital is less than the combined volume of these 1s orbitals and definitely less than the sigma 1s here. And so that's also going to raise the energy according to that Heisenberg uncertainty principle. And so it turns out just like this sigma 1s was lower in energy than the original 1s orbitals, this new molecular orbital is going to be higher in energy. And we'll call it the sigma 1s star. So, and it turns out that, again, these molecular orbitals, just like the original atomic orbitals, can each hold 2 electrons. Any orbital in the universe that you're ever likely to see is going to be able to hold a maximum of 2 electrons, whether that's atomic orbitals or these molecular orbitals. And so you can fit 2 electrons into this molecular orbital, you can fit 2 electrons into this molecular orbital. Well, in this case, would I rather put 2 electrons in this sigma 1s molecular orbital or just leave them as separate atoms in the 1s orbitals? Well, this is lower energy. And so according to Aufbau, you fill in the lowest energy orbitals first, and so I'd rather put them here. So, and that's what makes this bonding. So having this orbital that's lower in energy than the original atomic orbitals means that putting electrons there is likely to hold these atoms together into a molecule rather than them being separate apart. There's an advantage to being together. However, so this orbital right here is higher in energy than the original 1s orbitals, and so putting electrons in this orbital is worse than having the separate atoms. And so it serves to actually want the atoms to be just, say, separate and not come together when you put electrons here. And so as a result, we call it an antibonding molecular orbital. And this is where things get weird. So when you get the overlap between the atomic orbitals, it always simultaneously leads to the creation of both a lower energy bonding molecular orbital from constructive overlap and a higher energy antibonding molecular orbital from destructive overlap. Both occur simultaneously. And so notice the total number of orbitals you have is always going to be unchanged. So we started with 2 1s orbitals from 2 separate atoms. We had 2 orbitals. When they came together, those 1s orbitals ceased to exist once we form a molecule. What now exists are these molecular orbitals, but it's still a total of 2 orbitals. But that's what's really going on. And so here we're showing this with the 1s orbitals, and we'll draw a lovely MO diagram to correspond to this in a little bit. So, but the big thing is that, we're only going to consider what are called the homonuclear diatomics. And so we're actually only going to look at identical orbitals overlapping. So here we did it with an S and an S. In a little bit, we're going to do it with a P and a P in a couple of different ways, both sigma and pi versions of that. So, but in more complicated molecules, you might have, an S overlapping with a P, or maybe some hybrids you might consider, or something like this. And the truth is, it's actually even more complicated than that. Once you get into many atom systems beyond just 2 atoms, which is all we're going to consider in this lesson, so it turns out all the orbitals of all the atoms in the entire molecule are going to combine in different ways to form molecular orbitals. And this gets a little bit crazy to think about when you think about, proteins that can have thousands and thousands of atoms. And you're going to have like molecular orbitals that are some sort of combination of all the all the atomic orbitals of all those atoms. That's crazy. But it turns out there's a reality there. And it gets so complicated we can't even deal with it. But with things like methane, CH4, which has a carbon and 4 hydrogen atoms, 4 hydrogen atoms. So with that carbon and 4 hydrogen atoms, you've got 5 atoms orbitals overlapping, and we can actually plot out their molecular orbitals. And so just from, taking into account all the orbitals that are actually overlapping, and it's really complicated, and it's beyond the scope of what I'm going to present in this lesson. So, but again, it's complicated just for 5 atoms. Again, get to a protein where you've got thousands of atoms, and it gets insane, and it's nothing we can really visualize all that well in many cases. So, but again, this actually is going to give us a description of reality that's going to be pretty useful here. So, all right, so we've kind of looked at overlapping s orbitals, so and how it leads to the lower energy bonding molecular orbital from constructive overlap and the higher energy antibonding molecular orbital from destructive overlap. But let's see the same thing with p orbitals here. All right, so we're going to take a couple of atoms, and they're separate atoms right now with a p orbital. And this, it turns out, is the pz orbital. There's a p orbital that lies on the x-axis, one on the y-axis, one on the z-axis. And the one that's on the z-axis is going to undergo sigma overlap when they come to, these two atoms that come to approach each other. And in this case, one reminder on the p orbital is there's a node right at the nucleus. So for an electron in a p orbital, you will never find that electron at the nucleus. There's a node there. The function goes to 0. And it does, just like we saw with the sine function, because on one side of it, it'll take on positive values, and on the other side, negative values. And it could be positive on the left and negative on the right, or it could be, negative on the left and positive on the right. It's arbitrary. But they do have opposite signs, just like in the sine function. You pass through that node, and you're going through from positive values down to negative values, or you're going from negative values up to positive values when you cross through a value of 0 for the function. So in this case, instead of writing positives and negatives, though, what we often do is just do a difference in shading. And so the shading, one of the shading could be positive and not shading negative, or vice versa. We never actually go so far as to define it. We just need opposites in this case. And just a reminder again, this is not a charge. This is the math, so not plus and minus charges at all, but the mathematical sign of the function. And so in this case, I'm going to choose such a way where the lobes of the p orbital that have the same sign are going to be the actual ones overlapping. And so in this case, when these come to overlap, so again, this is the shaded region on this one, this is the shaded region on this one. And so where they're overlapping, they have the same mathematical sign, either both positive or both negative, and that's going to lead to constructive overlap. And just like it did back here with the s orbitals, constructive overlap's going to lead to a lower energy molecular orbital that is a bonding molecular orbital. And we kind of get an idea what this looks like here. And so this region where they overlapped got magnified, amplified, and again, that's all got that sign, whereas these have the other sign. And once again, you can see now in this new molecular orbital, this bonding molecular orbital we've created, you've got a change in sign of the function every time you cross a node. We go from one sign to 0 to a different sign to 0 to a different sign. And so we have those two nodes. Notice those two nodes were already present there at both nuclei, and they're still present at both nuclei. When you get constructive overlap, you don't create any new nodes. So if you started out with 2 nodes in the individual atomic orbitals, you're going to have 2 nodes in the overall molecular orbital. And again, you're going to get a region of amplification right in between the atoms. In this case, we'll call this the sigma 2p molecular orbital. So it turns out this is from, we don't have p orbitals in shell number 1, so this would be for a 2p. But again, just like we saw with the s orbitals, destructive overlap will occur at the same time, and we've got to consider both possibilities. So going back here, let's say we take this one on the left, and now we'll shade this side over here instead, and that's going to make this a little complicated, so I'm going to redraw it. And so we've got shading over here, but now we've got the shading over here. And so this region where they overlap now, so from the 2 different lobes of the 2 different p orbitals, they're going to have opposite signs, and they're going to cancel each other out. And it's going to create a new molecular orbital that's going to be antibonding and higher in energy. And once again, when I want to draw an antibonding molecular orbital, I do it the same way I did over here. I draw the bonding one, and then I just erase that region down the middle where they were having some destructive overlap. So I'm just going to redraw this guy right here. It's not a perfect drawing, so but suffice to say, we can see the creation of the new node. And if we show the shading, we go from not shading to shading to not shading to shading. And with the antibonding molecular orbital, destructive overlap is always going to lead to the creation of a new node right along between the 2 nuclei, along that internuclear axis, we say. And again, this is going to be higher energy because the best place for the electrons to be would be right in between the 2 nuclei, and that's the place where they can't be. And again, because we canceled out part of the orbital volume, if you will, it's also going to have lower volume and be higher energy according to the Heisenberg uncertainty principle. Cool. So before these atoms came together, we just had separate p orbitals. But once the atoms come together, those p orbitals no longer exist. Those atomic orbitals no longer exist. Because those atoms have come together to form a molecule, it's now these two molecular orbitals that exist. And again, you form the lower energy bonding one. You also form the higher energy antibonding, which we always designate with an asterisk. So this is sigma 2p, and this is either sigma 2p antibonding, some people would say, or most commonly you'll hear it called sigma 2p star, is the way they would refer to that. Cool, so now we've seen how p orbitals, and specifically the pz, can come together to do sigma overlap. So however, those two p orbitals are oriented in such a way that they would, when the atoms come together, they would overlap end to end, and that would be sigma overlap. But that's pz. What about like py and px? When the atoms come together, they're going to overlap in side-to-side fashion instead, and that would be pi overlap. And so let's take a look at that as well. And once again, we're going to have these atoms coming together. And so, for example, py, when these come together, we're going to get side-to-side overlap now. So, and one, we could consider the overlap to be in phase, in which case the areas where they overlap, and again with pi overlap, we get overlap in two regions. So, but the overlap occurring both here and here has the same sign, and it's going to lead to an amplified view here. And so there's our nuclei, and we're going to get something with a big region of electron density there, and a big region of electron density there, shaded up here, not shaded down here. And we still have a node right along the nuclei there, but we had that node to begin with in the original atomic orbitals as well. The big thing is that we have not created a new node right along this internuclear axis in between the nuclei. And again, that's going to be characteristic of your bonding molecular orbitals. You don't create a new node, you get constructive overlap rather than destructive. And this guy right here, we're just going to call the pi 2p molecular orbital. And again, just like any other molecular orbital, it can hold 2 electrons. So, but we've also got to consider the opposite case where we get destructive overlap, where the p orbitals that are approaching each other are exactly out of phase instead of in phase. So let's redraw that possibility. And so now all of a sudden, where we get the overlap occurring, they're exactly opposite signs, and they're going to cancel each other out. And if I want to draw what that would look like, again, my favorite way is just to draw the bonding molecular orbital and then erase that region right down the middle. So I'm going to run out of room here just a little bit. In fact, I'll redraw this in a second, just to give myself enough room. All right. We'll erase that region right down the middle. Again, not a perfect drawing, but it will suffice. And if we look at our shading here to designate our signs, it looks something like this. And so we still have that node right along the nuclei. You're always going to have that for a pi molecular orbital, so created from p orbitals. But we also have created a new node right down the middle along that axis between the nuclei, which we're always going to do for a antibonding molecular orbital. And so this is our pi 2p antibonding. So in here I showed it for kind of like py, but px would do the same thing instead of being on the vertical axis, on the horizontal axis as well. And so you end up creating 2 sets of these molecular orbitals from the 2p orbitals for x and y. So now we've got a better idea of what's actually going on when atoms approach each other, either if it's just hydrogen and we're dealing with, electrons in shell number 1, or if we're dealing with the period 2 elements, which not only will you have the s orbitals in shell 1, you'll have the s orbital in shell 2, and the p orbitals also overlapping either in sigma fashion, which I said I would redraw this. So sigma fashion or pi fashion. So now we've got to put this all together and create a what we call an MO diagram, a molecular orbital diagram for a variety of different molecules. So, but now we kind of got an idea of what these molecular orbitals look like, and you may be on the hook for identifying, looking at a picture and being like, what molecular orbital is that? Well, you'd have to look at this and be like, oh, that's the sigma overlap of p orbitals, that's the sigma 2p. So, or looking at something like this and be like, oh, that resulted from side to side overlap of p orbitals, but it was out of phase, so that's the pi 2p star, pi 2p antibonding. All right, so let's create some MO diagrams here. So we're going to represent the atomic orbitals with a box like we did with electron configurations, and we will do the same thing with the molecular orbitals. So we're not actually going to draw these shapes in that we saw created. So, but we know that when two atoms come together, in this case two hydrogen atoms, so come together, their s orbitals are going to overlap to create a lower energy bonding molecular orbital that we'd call sigma 1s, and a higher energy antibonding molecular orbital, which we'd call sigma 1s star. Now, in this case, we know that we had a total of 1 electron each for the hydrogens, a total of 2. And so we show on the same diagram, this gets a little confusing, but we're going to show both the before and after picture of bonding. So before they've come together to bond, these two separate atoms just have 1 electron in separate 1s orbitals. And so on the sides, we show right here the atomic orbital diagram. But now we're going to show the molecular orbital diagram right up the middle here. So there's really 2 points in time, before bonding, after bonding, and you really need to understand that there is 2 points in time. So we've shown where the electrons go before bonding, now we need to show where they go after bonding. Well, to fill in 2 electrons into the after bonding picture, the molecular orbital picture, you put them in the lowest energy spots, and so they got 2 openings here, and that's where those 2 electrons would go, kind of like just according to Aufbau principle we saw earlier, where you fill in the lowest energy spots first. And we can see now why hydrogen exists as a diatomic, because the after picture is lower in energy than the before picture. So the electrons end up lower in energy on average than the electrons of separate atoms, and that's why it bonds together. So typically things in the universe want to be as low in energy as possible, and processes that lower the energy of the universe and stuff like that tend to be spontaneous. So those are the kind of processes that happen. And so that's why 2 hydrogen atoms would want to bond together. It lowers the energy of their electrons. Now, if we compare this to diatomic helium, which does not exist, and we can explain why it doesn't exist now. So each of those heliums has 2 electrons in the 1s orbital now. And again, when they overlap, they're going to create a lower energy bonding molecular orbital and a higher energy antibonding molecular orbital. So, but now we've got 4 total electrons to fill into our molecular orbitals, and so we'll put the first 2 in the bonding, but we'll put the second 2 in the antibonding. And so it turns out, putting 2 electrons in a bonding molecular orbital, that's equivalent to a bond. If you recall, everything we've done so far, like with Lewis structures, says that there's 2 electrons in a single bond. And so putting 2 electrons in a bonding molecular orbital, that's equivalent to a bond. But putting 2 electrons in an antibonding molecular orbital kind of cancels that out. It's an anti-bond. And so in this case, we can see that, well, the 2 bonding electrons are canceled out by the 2 antibonding electrons, and so it's kind of like it has no bonds, which is why it doesn't exist. Now, we've created what's called the bond order as a way to kind of put a mathematical calculation on this. And so the way this works, for your bond order, you're going to take your number of bonding electrons, and again, you're going to just focus on the molecular orbital diagram, not the atomic part. So you'll take the number of bonding electrons, 2, subtract off the number of antibonding, in this case 0, and then divide by 2. And that's going to get you your bond order, which in this case 2 minus 0 is 2, divided by 2 is 1. And this would be a bond order of 1 is kind of the equivalent of a single bond of what you saw on a Lewis diagram. Cool, and so we see that, yeah, Lewis showed this as a single bond, and then molecular orbital theory kind of confirms that, yeah, it's essentially the equivalent of a single bond, this bond order. So when we do the same thing for helium, though, and I'll abbreviate this as BO, which might not have been the best choice, but in this case, we've got 2 bonding, 2 antibonding, so 2 minus 2, and then all over 2. And again, it's all over 2 because it takes 2 electrons to make a bond, essentially. So you just want to find out what's the balance of excess bonding electrons, and then divide by 2 to get the equivalent number of bonds that means. So, but in this case, it's just going to equal 0. And a bond order of 0 means there's no bond there, which means that this doesn't exist. There's no bond. This diatomic helium does not even exist. So typically, if you've got a positive bond order, anything higher than 0, we think there's a chance that that could exist. But a bond order of 0, that is something that does not exist. And so in this case, we've now explained, according to molecular orbital theory, why hydrogen is a diatomic, whereas helium is not a diatomic and doesn't exist as a diatomic. Cool, and this is kind of the way it works. Now notice, we could go and, start looking at different things. So we already talked about, so helium diatomic here doesn't exist. But what if I had helium diatomic with a plus charge? So with a plus charge, with ions, you're supposed to know that with cations you lose electrons, with anions you gain electrons. And so here with a diatomic helium cation, instead of having a total of 4 electrons, it would only have 3. And so it turns out in the atomic part, I can just choose whichever one I want to erase. It doesn't really matter. But in the molecular part, I have to erase one of the highest energy electrons, and I'd be left with a picture looking like this. And that's going to change our calculation for bond order now. And so we'd have 2 minus 1 all over 2, and we'd get a bond order of 1/2. And that's greater than 0. It's the equivalent of like half a bond, which we don't really have a Lewis structure analog for that. But because it's higher than 0, we might consider He2 plus as actually having a chance of existing, of there being some sort of correspondence to reality. So again, diatomic helium itself, not so much, but He2 plus, that might actually exist, again, because we do have a positive bond order associated with it. Cool, this is going to get a little more complicated when we start dealing with the period 2 elements. We're just going to have more molecular orbitals to kind of diagram out. Let's take a look. All right, so now we'll deal with the homonuclear diatomics for the period 2 elements, and we're going to start with O2, F2, Ne2, and that homonuclear just refers to 2 identical atoms, so 2 oxygens, 2 fluorines, 2 neons. There is such a thing as heteronuclear diatomics, like NO would be an example of that, but I'm going to totally not cover that. Most of you will not be on the hook for the heteronuclear diatomics. So if we look at these homonuclear diatomics, so it turns out that oxygen, fluorine, and neon, this is what the diagram would look like. You're going to get the 1s orbitals overlapping to create the lower energy bonding sigma 1s and the higher energy sigma 1s star antibonding. You're going to get the 2s orbitals overlapping in the same fashion, giving a lower energy sigma 2s and a higher energy sigma 2s antibonding. Then you're going to get the p orbitals overlapping, and the pz's are going to overlap end to end to give the lower energy sigma 2p and higher energy sigma 2p antibonding. But then px and py, when they overlap side to side, it's going to lead to lower energy pi 2p molecular orbitals and pi 2p star antibonding molecular orbitals that are higher energy. So this is what the diagram would look like. Now we'll find out for everybody left of oxygen on the periodic table in period 2 there, the diagram's going to switch just a little bit, and we'll talk about why and point it out and stuff like this. But this is the diagram we've got to fill in. So if we take a look at starting with, say, oxygen, well, oxygen's 1s2, 2s2, 2p4. And so that's what each of the oxygens are going to look like. Now, one thing to note, let's just deal with those 1s electrons for a second. So those 1s electrons are full. And because they're full, then when they overlap, and those, again, 1s orbitals cease to exist, you will end up filling both the sigma 1s and the sigma 1s antibonding. And that's not going to really tell us much because the bonding molecular orbital electrons are going to get canceled out by the antibonding ones. And so it's not going to contribute to the bond order. And so the truth is, a lot of times we'll just leave out the core electrons off the diagram and only diagram out the valence because, again, these aren't really going to contribute. The electrons are always going to be paired up. They're always going to cancel each other out in terms of a bond order calculation. And so they don't really tell us anything we don't already know. And so oftentimes you'll just see this kind of eliminated. I drew it in once. I probably won't draw it on the next diagram, as you'll see. But here, now we can focus on these valence electrons. And so 2s2. And so 4 electrons total, so we'll fill in 2 here and 2 here. But the p electrons are not full. We've got 4 for each of the oxygens, so 1, 2, 3, 4, 1, 2, 3, 4. And so we've got a total of 8 electrons to fill into the molecular orbitals, and we'll just work our way up. So first 2 go here, 1, 2, and then the pi 2p's here are degenerate, and when you've got degenerate orbitals, everybody gets 1 before you start pairing them up. That's 2, 4, 6, and we've got 8. So once again, we'll put electrons right there. Cool, and this is what the structure, the MO diagram here for O2 looks like. Now this tells us a couple of things. So one, if we take a look at that bond order calculation, so in this case, and if we do for the whole thing, we could be like let's go, bonding 2, 4, 6, 8, 10, and then 2, 4, 5, 6, all over 2 is going to get us a bond order of 2. And if we just left off the core electrons entirely and redid the calculation, so leaving those out, we would have had 2, 4, 6, 8 bonding, and then 2, 4 antibonding. And so instead of 10 minus 6, we would have got 8 minus 4. Both numbers would have just been reduced by 2, but it would still lead us to getting a bond order calculation of 2. And so that's what I meant by, leaving these out of the bond order calculation and stuff like that doesn't tell us anything we don't already know. You're going to get the same calculation of bond order, but this tells us that this has the equivalent in O2 of a double bond, and that corresponds nicely with what we know about the Lewis structure. So the Lewis structure even shows a double bond, and this corresponds to a bond order of 2, and so this confirms, or at least is consistent with what we know of the Lewis structure, but it tells us something the Lewis structure does not. So we got a couple new vocab words here. So one is paramagnetic, and one is diamagnetic. So it turns out for a paramagnetic substance, it is attracted in a magnetic field, whereas for a diamagnetic, it has a very, very, very weak repulsion in a magnet when placed in a magnetic field. And what causes this is the presence or absence of unpaired electrons. So it turns out electrons, you learned, have a spin associated with them, but when you pair up electrons, their spins are opposites and they cancel. And so it turns out if all your electrons are paired up, then their spins all cancel, and you don't experience an attraction in the magnetic field. In fact, you get that really, really weak repulsion, it turns out, and that's what makes you diamagnetic. All your electrons are paired, there's not a single unpaired electron to be found in you. So, and if we look at the Lewis structure, it looks like all the electrons exist in pairs. So pair and a bond there, pair and a bond there, a lone pair, lone pair, lone pair, lone pair. And according to the Lewis structure, we might think that O2 is diamagnetic. Unfortunately, though, it does experience an attraction when placed in a magnetic field, and Lewis is not going to help us understand that, but molecular orbital theory will. We can see here we've got 2 unpaired electrons in the pi 2p star antibonding molecular orbital, and so molecular orbital theory allows us to figure out that yeah, O2 is indeed paramagnetic as we know in practice, and now we can explain why. And before we got to MO theory, we couldn't explain why. And so here's one of the big successes of MO theory over the earlier bonding theories. It allows us to predict paramagnetism and diamagnetism better than the earlier bonding theories like the Lewis theory in this case. Okay, let's say we switch this up and take a look at F2. If we draw the Lewis structure in F2, so this is what it looks like, and it looks like it has a single bond, and we'll find that that's going to correspond to a bond order of 1 in a little bit. And it turns out that F2 is diamagnetic, and so hopefully we'll realize from the MO diagram in a second that it doesn't have any unpaired electrons. And if we take a look at fluorine here, we got 1s2, 2s2, 2p5. And so how would this be different than what we saw with oxygen? Well, all we'd have to do is add 1 more electron in to the 2p orbitals. And adding 1 more there means we have to add in, so 1 more for each of these, add in another 2 electrons to the MO diagram, which means adding them in there. And so now if we go to do our bond order calculation, well, we just added 2 more antibonding electrons. And so instead of 8 minus 4 over 2, it's now going to be 8 minus 6 over 2, which equals 1. And so F2 has a bond order of 1, which is consistent with the single bond we know exists according to Lewis structures, and life is good. We also see that all the electrons are now paired up, and F2, we can explain that, yeah, it's consistent with the idea that it is indeed diamagnetic. Now, if we move on to neon here, and notice we wrote neon too, but notice neon being a noble gas doesn't exist as a diatomic. And so we're not going to explain any properties of neon 2. We're going to explain again, just like we did with helium, why it doesn't exist. Diatomic neon does not exist either. And in this case, we move on to neon. 1s2, 2s2, 2p6. And we'd have to, again, add one additional electron for each of the neon atoms, which means 2 additional electrons into the MO diagram. And now we see when we go to calculate out that bond order, we've now got, again, looking at just the valence, 2, 4, 6, 8 bonding and 2, 4, 6, 8 anti-bonding. And 8 minus 8 over 2 is a 0. And with a 0 bond order, we predict that it does not exist. And so we also can use here molecular orbital theory to show that Ne2 is not something we'd anticipate existing. Okay, so again, this is the MO diagram for O2, F2, Ne2. But if you want to take a look at everybody left of oxygen, so N2, C2, B2, Be2, or Li2 in those period 2 elements, we're going to have to switch up the diagram just a little bit. Let's take a look. All right, so here I've got the MO diagram now for the other period 2 homonuclear diatomics. And we see one major change here, and that major change here is the sigma 2p and pi 2p's have switched places. So if you notice here, this was nice because it was all symmetrical. So you had the pi 2p lower in energy than the original 2p atomic orbitals, just as the pi 2p star was just as equally high in energy above those 2p orbitals. And same thing with the sigma 2p and sigma 2p star. And so there was this nice symmetry here, and that symmetry is now broken. So, and again, reality is often more complicated than we'd like it to be. So, but it turns out with fewer electrons in the p orbitals, so it turns out the screening that's going on here is actually going to lead for these lovely elements here, for the 2s and the 2p to be closer in energy than they were over here for oxygen, fluorine, or neon. So in having them be closer in energy has some significant impacts. It turns out that when orbitals are overlapping in this kind of MO fashion, they have to be somewhat similar in energy for there to be any kind of meaningful overlap. And so in the case here, this 2s orbital right here and one of the 2pz that's up here are so far apart that there's really no meaningful overlap going on there. But here, they're much closer in energy now, and as a result, so your 2s orbitals not only overlap with each other, but the 2s orbital of one can overlap with the 2pz of the other. And so what that ultimately does is it's going to actually increase, or really just increase the separation here between the sigma 2p here, raising it higher in energy above that of the pi 2p. So that's why these are switched here, and we call this sp mixing. So here with the 2s and the 2p's, their energy being far enough apart, we really don't consider any significant amount of sp mixing. But for the rest of these elements in period 2, because the 2s and 2p are much closer in energy, we will have this sp mixing. One thing to note here, I did leave the 1s off, just like I said I probably would, because it doesn't really contribute anything to our understanding. So I'm going to be looking at just the valence electrons here. Cool. So this is our diagram here. We don't have to work all of these, but I do want to work one of them, and that one I want to work is nitrogen. So because we know something about diatomic nitrogen. Now these other diatomics, I don't know that we really encounter in significant fashion, especially for some of these like lithium's a metal and stuff. So, but diatomic nitrogen, that's the biggest portion of the air that you're breathing right now. Yes, there's oxygen, that's the stuff you need, but 78% of that air is nitrogen, that's diatomic nitrogen. And we know, according to Mr. Lewis, we diagram it out to look like this, and it has a triple bond. And if we take a look at the electron configuration for nitrogen, so 1s2, 2s2, 2p3, having that half-filled p subshell. And again, we're only going to focus on the valence electrons here, and so we got to fill those in, and we've got 2s2. So 2 electrons there for each of these nitrogen atoms. And what that means is we'll fill in the sigma 2s and the sigma 2s antibonding. So there's those 4 electrons are now filled in here on the molecular part of the diagram. And then we've got 2p3. So we've got an electron on each of the p orbitals for both nitrogens. And so we've got 6 total p electrons to fill in. And the first 4, well, let's get those with the correct spin. That would be disastrous. First 4 go there, and then 5, 6. And we go to calculate our bond order now. And we've got 2, 4, 6, 8 bonding electrons and only 2 antibonding. So 8 minus 2 all over 2 equals 3. And a bond order of 3 does indeed correspond to what Lewis would have us draw as a triple bond. And so it's consistent with that. And notice all of our electrons are also paired in the molecular orbital part of the diagram. And so we'd expect N2, MO theory would predict it to be diamagnetic, and indeed it is. So great, this is pretty much the level of MO theory you've got to understand. So you should know, again, here's the diagram. You should know that we've got the atomic part of the diagram before atoms, separate atoms before they're bonded together. And then we have the molecular part of the diagram down the middle. So a lot of students don't get that and they get lost on filling in the electrons. But the electrons that are filled into the atoms are the same electrons that are filled into the molecule here. But it's only the molecule that exists after they come together. It's only the atoms that would exist before they've come together. But we're representing both realities at the same time on the same diagram. You should be able to calculate bond orders. You should know what those molecular orbitals look like, both the bonding and the antibonding that we drew out earlier. So both like the sigma, and sigma star for the s orbitals, the sigma and sigma star for the p orbitals, and then the pi and the pi stars for those p orbitals as well. Finally, you should be able to draw the MO diagram for any one of the homonuclear diatomics. And some of you will be on the hook for actually knowing which diagram you need to use for which of these, but quite a few of you are probably actually going to even be provided the appropriate diagram, and go from there. So you should ask your professor and ask him or her, am I going to have to memorize these lovely MO diagrams for all the period 2 homonuclear diatomics? And do I have to know which follows this and which follows this, or will they be provided for you and you just need to know how to fill them in? And again, most of you probably will just have to fill them in, but some of you will be on the hook for actually memorizing the diagrams. My apologies if that's the case for you. Now, if you found this lesson helpful, would you consider hitting that like button? Best thing you can do to make sure other students get to see this lesson as well. And if not, you should just smile, because hopefully MO theory is just a little more understandable than it was 40 minutes ago. Happy studying.